Okay, last time we talked about discrete random variables where we had a fixed number of outcomes. We represent those outcomes with a number, and then we listed the probability of each outcome. Now we're going to talk about continuous random variables. So discrete random variables came from situations that require you to count something. So usually they're like our nice, pretty whole numbers. Situations that involve measuring something often result in that continuous random variable. And so a continuous random variable will take any value in an interval. So now we can start seeing the decimals and any values sort of happening in between. Now the probability distribution of that continuous random variable is going to be shown by a density curve. And more often than not, our density curve is going to be a normal distribution. So you're going to see a lot of those normal curves popping back up, and then using our normal CDFs to help calculate the probabilities. Now, the probability of any event is the area under the density curve and above or below a value of x. So we're going to start seeing those normal curves. We're going to say, okay, what's the probability it's here and higher? Or what's the probability with our normal curve? That's a horrible normal curve, that it's between here and here. And so we're going to be calculating those types of things. Now our probability model of a discrete random variable assigns a probability between 0 and 1 for each possible value. And a continuous random variable has infinitely many possible values, which means that not every value in that interval will be represented. So pretty much it's going to be impossible to find the probability of getting one exact value. So all continuous probability models assign a probability of 0 for just a specific outcome, because we really don't know if we're going to get that outcome or not. So we look at the probability of an outcome in a range or an interval of values. And so only that interval will have a numerical probability, which is why we do normal CDFs instead of PDFs. So when you look at your calculator under the distribution menu, a CDF is a cumulative frequency. So it's kind of adding up all the probabilities in between there, or possible probabilities. But a PDF looks at specific things and it's a little different. It's actually looking at a point value on your curve, and we really don't want to work with that. That's why we do the CDFs. Okay, so sample problem. The heights of young women closely follow a normal distribution. Normal distribution with a mean of 64 inches. That means when we come to our normal curve, our mean would be 64 inches. And a standard deviation of 2.7 inches. So here's our mean. Here's our standard deviation. This is a distribution for a large set of data. Now choose one young woman at random. We're going to call her height y. If we repeat a random choice very many times, the distribution of the values y is the same as the normal distribution that describes the heights of all young women. Find the probability that the chosen woman is between 68 and 70 inches tall. So we want the probability that our y is between 68 and 70 inches tall. So this is what we're going to calculate. The y is between 68 and 70. And we're going to do that because we know it's a normal distribution. We're going to calculate a normal CDF on our calculator that's under the distribution menu. And then we have to label in what we're typing in as our boundary information. So our lower bound is 68. Our upper bound is 70. Now to help scale out how does our curve look, we also need to say what our mean and standard deviation is. So our mean is going to be 64, and our standard deviation is going to be 2.7. And so this will allow us to calculate that normal CDF. So on that, we get a value of 0.0561. And we have to practice interpreting what this means. The probability a woman's height, that's what we're talking about, is between 68 and 70 inches. Is about 5.61%. And that's it. Okay, so on our next one, now we don't have the curve, well, we have a curve drawn for us, but we're going to have to label it out. So we're looking at the weights of 3-year-old females. The weights of 3-year-old females closely follow a normal distribution with a mean of 30.7. So right here, we've got 30.7 and a standard deviation of 3.6 pounds. So that means each little marking is a standard deviation that would go up by 3.6 pounds. So we've got 34.3, we've got 37.9 and 41.5. And then we'd go down by 3.6, so 27.1 and 23.5 and 19.9. And it's a really good idea to draw out these. In fact, a lot of times you get kind of extra points, and it helps you catch a mistake when you have this on a test. So we want to know, randomly choose one 3-year-old female and call her weight X. Find the probability that the randomly selected 3-year-old female weighs at least 30 pounds. So at least means the lowest is 30 pounds, so my probability of the weight is at least 30 pounds. This is the probability I'm going to calculate. So when I look at my normal curve, I'm going to find about 30 pounds, and I want everything above it. And we can tell right away that that probability is right around half, a little bit more than half of that curve. So I know that when I'm calculating it, if I end up with something bigger, like 80%, I've done something wrong. Or if I end up with something really small, I've done something wrong. And that's why they like you to draw out those curves, is so you can get an idea of what's happening and you can understand where your mistakes may be happening. So we are going to calculate this with a normal CTF. And for time purposes, we're going to go ahead and label this as a lower bound LB, but on a test or quiz, you need to write that out. Our lower bound is 30. So it's the lowest number that we can go by. Our upper bound has to be something really high, and this is why another reason why it's good to have our normal curve. We want it to be really high. So if my highest value here is 41.5, I want something even bigger than that. So I'm going to go really big. I'm going to say 100. And then my mean is 30.7, and my standard deviation is 3.6. So we plug that in our calculator, and we get a probability of 0.5771, which looks pretty correct, close to that 50%. We can tell by the shading. So then we interpret it, probability that a randomly selected 3-year-old weighs at least 30 pounds, 3-year-old female. Okay, so 3-year-old female weighs at least 30 pounds. Is 57.71%. And that's it.